Good morning, everyone. I'm Ademola Adetunji, and research associate with the Meta Earth. So I would be talking to you about the recent updates in the Meta Earth MT projects. The Magnetotelluric is shortened for MT, so that's what I mean when I say MT. So I will focus mainly on the recent data acquired around Geraldton, Red Lake, and Timmins Transect. We'll touch on the data quality, the preliminary models produced for the purpose of this meeting, inferences that can be drawn from such models, as well as the future plan for the projects. So between September last year and a couple of weeks ago, 2 weeks ago precisely, we acquired a new set of data, 36 AMT precisely, from Red Lake. AMT, that's the audio frequency magnetotelluric data that focuses on the top few kilometers of the Earth. And in addition, we acquired 140 broadband MT sites from Geraldton, Red Lake, and Timmins. Broadband MT, they give more information about mid and lower crust, well, extend basically from the top few kilometers to the Moho. And taken together, we spent about $500,000 on this project. So with that, we have increased the number of Meta Earth transects to 15, consisting of 925 MT stations. 367 of those are AMT, while 559 are broadband stations. The green area, this is the Red Lake, the new transect, and the Timmins, another new transect. This is the Geraldton, the updated transect. All the black ones are the existing Meta Earth transects. So going to Geraldton, the blue dots indicate the existing MT data from this region. And the triangles are the newly acquired data. So the data were acquired simply to provide 3D control for the result produced by the previous data set. So why did we need to do that? Here are the depth slices from the models. The model produced using the previous data set shown in black dots. One striking feature is this very large scale conductivity anomaly that cannot be explained by the existing data set. The level of confidence in it is very low, and so many other structures as well with that in mind. So we went back to the field to add more data so that we can better constrain this structure and have a general idea of what it looks like and be able to interpret in three-dimensional space. So here are the depth slices from the new model produced from a combination of the old and the new data set. And as you can see, now we have better constraint. We can confidently interpret this structure because it's data constraint. The RA in charge of this transect, Suzanne, will discuss these models with you in more details. So I will leave it at that and go to Red Lake. So at Red Lake, we collected a total of 36 AMT. All our AMT data set were acquired here. It runs through the gold district in this region. So the green dots, the AMT sites, spaced at about 500 meters apart. We have a few 3D control sites. Sometimes it's less or more than 500, depending on the access and culture around the area. Typically, the high frequency component from 10,000 to 10 hertz, and the data quality in this region is not really encouraging, especially the TIPA component, and that's basically due to the cultural noise that is everywhere, infrastructures and mining activities going on during the field campaign. But with that, even for the purpose of this meeting, so I use only the impedances that are fairly clean to produce a 3D model. And well, we can see a little bit of stuff in the result. These feature in circle. These are the This is around the Balma town, a very popular mining district with a lot of shafts and mining camps there. And it's termed the Campbell Red Lake ore deposits this region, and this is called the H.G. Young ore deposit. And that's from the relative to the geological model produced by this Evolution Mining Company. Just screen grab this from a talk I attended. So that's all I have for the AMT at the moment. We have other structures there. I don't know what they are right now, but this is in its infancy at the moment, still working on it. And so going to the MT, we have 45 MT sites distributed roughly along the lithoprobe seismic line in this region. We have quite a few 3D control sites in case we have features that trending in different directions. They are roughly spaced at 2.5 kilometers apart. And the data quality, especially around the center here, is also very highly affected by infrastructure and mining activity. This map here shows the new Red Lake Transects, MT Transect, basically at the moment, with all the MT data, the broadband and the AMT at the center here. Now, about the data quality, like I mentioned, there are sanding curves, the impedances, and the TIPA data for a site at the south and a site at the north, away from the center. As we can see, the impedances, they look good, very useful, but as we approach the center, we have a series of problems. In this case, we can use only half of this data, or in this case, we cannot use this impedance at all for the inversion because it's heavily distorted. And in all cases, the TIPA, they are not encouraging. We'll salvage as much as we can, but that's just what the data looks like. But then we cleaned up the impedances for all the 45 sites, threw away a couple of sites and produced a model, 3D model, just to see what we have spent the money on. And it's not that bad. So we have very encouraging features. This is from very shallow depth, 1.822 kilometers all the way to lower crust. This feature is termed C1. This is along along strike with the Palmer Town, the Campbell ore deposit that I mentioned earlier. We have others labeled as C2, 3, by C I mean conductivity anomaly, and 4. So I have other features deep in, we don't know what all those are at the moment. And looking at the vertical sections through these lines, this is what the 3D view looks like. It's in Fence diagram, and this is C1, the C2 that I mentioned earlier, 3, and 4. Again, I'm not assigning interpretation to all of these at the moment, just looking at what the data has to offer. And so the black line indicates the seismic profile through this region. This is the lithoprobe WS2B. And so we produce the seismic section overlaid with the geology and the MT section along this region in their true position. And this area right here corresponds to the Dixie Lake gold trend, and the region here is the Burma-Kochina mine trend. And unfolding these, straightening these out for better. So the C2 mentioned earlier corresponds to the Dixie Lake gold trend, and C1 corresponds to the Burma. So that's all we are. There are other fingers all around that we're still going to look into to see what they really represent. They all have common, and these represent the general superior province interpretation in terms of resistive upper crust and the conductive mid to lower crust generally. Now, so then going to Timmins, a bunch of companies came together to collect about 281 AMT data sets in and around Timmins during, they were collected concurrently with our own MT. And we have access to all these sites, but we're not doing anything with them as of yet. This is for the Canadian nickel company. This is for International Explorer, the Pan American Silver, and Newmont. The IM gold is a little bit off the scale of this map, further to the southwest. They all high frequency and they all look good. So this map here shows the relative position of all the AMT sites that I've just shown you. And all the blue dots are the Meta Earth MT sites in this region. We wanted to put one AMT line around here when we planned this project, but since Newmont came up with their idea, so we shelved that. Now zooming in into the Meta Earth, this is we have a total of 80 MT stations. 19 of those are in-kind contribution by Contact Geosciences, a company who did the data acquisition for us. Some of those sites, they align with the existing discoverability seismic lines in that region. This is the Rochester line, the South Timmins line, and the South Porcupine line. They have typical, and the data extend further, even deeper than the usual MT band. It goes all the way to 2,500 seconds in most cases, and the data quality is generally good, way better than what we had at Lake. So this right here is the plot of the off-diagonal impedances for all the sites at once. We can see a little bit of trending, rolling off the quadrants and some scatters around there. So, but easy to clean that up, really, for the purpose of the first set of inversion. And here are the maps of the TIPA at 4 different periods representing the different depths in this region. This was plotted based on using Parkinson convention, where all the arrows point towards possible location of conductors in the region. And inferences from this TIPA alone shows that we could have, because of the reversal around here, we could have a conductive anomaly in here and large scale conductors around here, and possibly now deepen in this direction as we go way deeper. So taking together both the impedances and the TIPA data, we created a 3D inversion using the mode EM. I'm trying to skip all the details here so that I can finish the talk on time. So here are 5 depth slices from basically shallow, which is not particularly very reliable for this kind of data, to really deep, the lower cross depth. The black lines are the seismic lines that I mentioned earlier on. And even at that, we can see the anomaly indicated on the TIPA earlier. And here, this place corresponds to the Porcupine Dexter deformation zone. The large scale anomalies with the imprint starting from very shallow depth all the way to greater depth, and other anomalies of interest to the north and to the south. And also looking at vertical sections through the model. This is what it looks like, but then I can, there are very large scale conductivity anomaly that typically dips to the north and all around the place, and so many fingers coming up from the lower cross. I will quickly play you just a second there. Okay, so this is depth slices, vertical varying with depth as we go to depth. And if we move from south to north, sorry there. Okay, the variation of the structure as we go towards the north from the south. And there are so many interesting structures in there so far. And from west to east, which is equivalent to the fence diagram that I showed you. So with that in mind, so now I want to show you a few slides that compare the interpreted seismic sections from the Snyder et al. 2005 paper to the current MT sections that we have. But for the South Porcupine, it's really short. So I would extend the line further south, especially to image the structure of interest indicated by my chipper in here. Now, this is interpreted section, again, from Snyder 2005 for the Crotchest line. Sorry, yeah, I should go back for the Crotchest line. So at the same scale, but vertical exaggeration of 2, which makes comparison really difficult. But if we look at it at a much larger scale, crosser scale section for the same line, we can see the very high level of similarity in the structures and that we have around there. I don't know what they are at the moment, but so far the inversion looks really good and stable, and the structure are reasonably reliable. And again, they correspond really well with the seismic. Again, this is for the South Timmins line. Again, at the same scale, looking at it, the Porcupine Destor really comes up really good. We have a very similar structures in both models. And again, looking at it at the large scale, this is the deformation zone, and we have some sort of intrusive body here, and the large scale conductivity anomaly that dips to the north is right there. The third one, the Porcupine Destor, like I said, I extended that further to the south. So there's a very, very interesting feature is the fault here that aligns very well with this boundary here. And again, the crosser scale, this is a structure of interest, and the fault that might correspond to these. And so I can't stop but ask myself whether this corresponds to shore dome, and this is a buried pluton in this region. So now we'll go into further data analysis and inversion and more rigorous testing to ascertain the position of all the structures, make sure they are true, and combine the result with other data that might be available to create geologic model and comprehensive interpretation. Thank you.
Great, thanks very much, Ademola. There's a question in the chat room here from Phil, and we're to the Red Lake area. Are the hydroelectric power lines the main noise problem, or maybe you can comment on what was causing the noise?
Yes, the hydro power line, they were the first set of problem we had, especially for the AMT. We couldn't move away from most of those lines. But not just that, we have a lot of buried infrastructures in the region, pipelines and what have you. For Red Lake, we repeated most of those stations several times until we couldn't try anymore, as each site would cost $3,000 and to repeat $4,000. So we stopped repeating. There are so many blastings going on around there, mine blastings and all that. Other sources of noise that we don't know, especially for the TPA, that really affected everything in and around the area. So when we were doing the MTA at a later stage, we tried to create as much as 2.5 kilometers away from all major power lines, but we still couldn't avoid everything.